to present online today. In fact, Hai and I know each other for a really long time. Hai graduated in, I think, 2014, got your PhD in 2014 from Swinburne Uni, and I received my PhD 3 years later in 2017. We were in the same group from Swinburne at that time. I also received a lot of guidelines and the support from Professor Mann. Really, it has been really a great time in Swinburne. And today, my topic. Let me share my screen. Yeah, can you see my screen?
Yes, all good. Thank you.
Okay, good. Okay, so today my topic is time-guaranteed cooperative control of multi-agent system and its application to connected automated vehicles. So basically, my talk will have two parts. Part one, I will introduce some key results in the time-guaranteed cooperative control, and in the second part, I will specifically focus on the application to the CAV, the connected automated vehicles. And finally, I will give some future research directions. So first, I will briefly show some background and the motivation of why we are doing research in the cooperative control of multi-agent system. And the concept of a multi-agent system stems from a variety of biological and social phenomena, as shown in these four images. You can see we have different biological and social phenomena, such as the schooling of fish, migration of the wild geese, the ant colonies, and also the swarming sheep. I would like to particularly introduce this wild geese. You can see when they fly in the sky, they can build some specific formation, but for each goose, they only use the information from the leader goose and the neighboring goose. But as a whole team, they can build some specific formation. And the multi-agent system just get inspired from this kind of phenomena. So this is the multi-agent system. And the official definition of a multi-agent system, we can say it's a system that consists of multiple autonomous agents. And those agents, they can communicate with each other through a network. And as a whole team, the system can accomplish some global coordinated task to achieve a desired behavior. And when we talk about the multi-agent system, the agent can be a lot of things. It can be the mobile robots on the ground. It can also be the drones in the sky and also some underwater vehicles. All these different uh, things can be called agent. Okay, and a nature question would be asked because for multi-agent systems, the key word is multi. So why we consider the multiple agents instead of just a single agent? I can so we have listed four different motivations. I would like to specifically mention the first one, the spatial distribution of the task, which means for some in the reality, uh, a lot of for some environment is too large and it's almost impossible for a single agent to accomplish the task. So, and also at the same time, for some, if you have only a single agent, if you fail, the whole team fail. But if you have multiple number of agents. If one team member fails, the other team members can cover you up. So which means the research in multi-agent system is not just because of the elegant, but because it's necessary to doing this kind of research. So in the cooperative control of multi-agent system, there are some common issues, I would say. Basically, there are three different common issues. The first one is the system dynamics. The second one is the guaranteed performance. And the last one is the information flow structure. So let's focus on the first one, the system dynamics. When we talk about the multi-agent system, the agent itself can be a lot of things, as mentioned previously. It can be the mobile robots, the drones, and the water vehicles, which means the agent dynamics can be fundamentally different from one case to another, and the dynamics can be the first order, second order, high order, or even nonlinear in reality. And also for the system, usually when we're doing the modeling, we can provide some mathematical modeling, but those modeling cannot accurately describe this system in practice. So which means we have to deal with some unknown parameters, the external disturbances, and also the model uncertainty. All these kind of things we have to take into account when we design the cooperative controllers. The next issue is about the guaranteed performance. The first one is about the user-defined performance, which means when we, as a control engineer, when we design some new controllers, we have to consider the cost. If you want to have a very accurate tracking performance, usually the calculation cost or the design cost would be high. So which means we want to adjust this kind of performance based on different users, different performance requirement. We can give different control strategies. So which means we want to make sure our controllers can be adaptive to different kind of scenarios. The second thing is about the global information. One of the key feature for cooperative control of multi-agent system is its distributive capability, which means that we do not want the global information. We only want some local interaction, as mentioned previously in the wild geese. For each goose, they only interact with their local neighbors and occasionally with the leader. So this is the no global information requirement for the second key issue in cooperative control. Next is the information flow structure. For the information flow, we typically have two different topologies. The one is undirected, the other is directed. Depending on different application areas, these two topologies can cover most of the cases. The other thing about the information flow is the network structure. For a multi-agent system, we can consider the leader following case, which again, I would like to use the wild geese the phenomena as an example. In that case, there is one leader, so the remaining geese just follow the leader goose. So as a whole team, they can accomplish this kind of leader following uh, task. There are also some other cases like leaderless cooperative control, which means there is no leader and every single agent, they just need to cooperate with each other, and as finally they achieve consensus, for example. And another case we call the multiple leader case. In the wild geese case, you have one leader, but it's also possible for a group you have multiple leaders. So when there are multiple leaders, how to design the cooperative controller can be also very challenging. And in fact, we can this is cooperative control. And in the same network, sometimes the interaction can be negative, which will result in some bipartite consensus problems. All these kind of different problems we can address in the cooperative control of multi-agent system. So we have talked about the cooperative control of multi-agent system. Then for all these, all the previous mentioned cooperative control, multi-agent system, the network cyber physical system, what really matters is not just the coordination can be accomplished, but also not just whether the coordination occurs. What's more important, I mean, is when the coordination occurs. Think about that. If you design some controller and if it takes 2 hours to accomplish the coordination, then it will sometimes make no sense because because the time will be very critical in some scenarios. For example, we want to all the agents meet in the same location within a specific time. For example, maybe like 10 minutes. But if you design the controller using 2 hours to reach that goal, then the task cannot really be accomplished. Okay, so that is a core issue in the cooperative control. So and also in conventional control strategies, there are many controllers designed to achieve the asymptotic as exponential convergence without formal settling time guaranteeing. And here, what my topic is called the time guaranteed. So, what does this time guaranteed mean? So here we have basically two different approach. The first approach is we call the fixed time cooperative control, which means the convergence will have a uniform bounded time. The second type of the approach is called the prescribed time cooperative control. And for the second case, the convergence is usually within a user designed deadline. And this kind of time guaranteed approach has a lot of system level significance, such as the safety, the scheduling, the certification, all these kind of things. I mean, in the system level, very important. Later, I will have some example to show you this. Okay, next, I would like to introduce some of our key results in this topic. And this slide will just summarize our core contributions in this time guaranteed cooperative control. Basically, we establish the fixed time and prescribed time consensus methods. We introduce some time-based generators design to make sure the convergence can be achieved within some user-defined time. And of course, as mentioned, a lot of systems, they will have the uncertainties, the external disturbances. We need to taking all these kind of things into account when designing our controllers. And also, we have in the last few years, we have published a number of high impact survey papers help the researchers in this field can have a very quick pickup about this kind of time guaranteed techniques. And yeah, so this slide is just shows our the core contributions. Now, I would like to give one simple example to show how the cooperative controller works. Let's assume an agent I with a very simple dynamic, the single integrator dynamics. Dot xi equal ui. Okay, so and for xi, it's the state of the agent, and the UI is a controller to be designed, and the cooperative control of consensus can be achieved by using UI equals the negative sum from j equal 1 to n, okay, and aij bracket xi minus xj. So here the key part is the aij is a weight between neighboring agents from xi to xj. With this kind of controller, the consensus can be achieved when the time approach infinity. So this is a conventional cooperative controller UI. I just want to take this to as a simple example to illustrate the motivation. Okay, next let's have a look. The previous one as mentioned, when we design that UI, the consensus can be achieved when the time t approach infinity. So here, because our topic is time guaranteed, we want to make sure the convergence is achieved within some specific time. So the first type of the controller, the time guaranteed controller, is we call the fixed time consensus controller. So here on this slide, we provide two different types of fixed time consensus controllers. Type 1 controller, you can there are type 1 and type 2. So type 1, you can see we add some power calculation. So on top of the neighboring, doing xj minus xi, and after all this kind of neighboring summation, we do a power calculation. We add the power index of P over Q, and this P is designed to be bigger than Q. Make sure this term is bigger than 1. Okay, and so for type 1, we do the summation before the power calculation, and for the type 2, on the other hand, we do the power calculation for each edge of, for example, xij for that edge, and after the power calculation, we do the summation. So that is the difference between the type 1 and the type 2, those two fixed time consensus controllers. And for type 1, we call it node-based controller, and type 2 is edge-based controller. And the different types, they can dealing with different scenarios. Okay, of course, this for this type 1, type 2, the alpha beta, they are required to be positive number, and the PQ UV are some odd integers. Next, we in this slide we introduce some pre-discrete time consensus controller. So pre-discrete time controller is slightly different from the previous one. So the key feature for this kind of pre-discrete time controller is we introduce a time-based generator. You can see on this image, we introduce the T, which is the TBG, the time-based generator, and this T is starting from 0 when t is 0, and it will increase until t equal 4, and that 4, t equal 4 is user-defined time. In reality, you can change that 4 to some other desired time, like 40 or 400, okay, depending on the system requirement. So this kind of time-based generator, TBG, is time varying. Okay, so based on the TBG, we add that part on top of the original consensus controller. So basically we introduce this time varying gain for the when we're doing the summation. Okay, and in this case, the settling time we call TF can it will be a prescribed time instant for arbitrary initial condition. And I would like to use this to plots to show the difference between the fixed time and the prescribed time controllers. So on these two plots, they are the results from the fixed time controllers. Okay, inside the circle, you can see on the right hand side, it's the energy consumed using the fixed time controller, and on the left hand side, it's inside the right circle. It's the trajectory. It's the control inputs of the system, which means it consumed more than 200 in terms of the energy. On the other hand, if we apply the prescribed time controller, the energy consumed has been significantly decreased. Okay, and also on the left hand side, you can see that the control inputs is the magnitude of the maximum control input is about 7. On the other hand, when we using the fixed time one, the maximum magnitude is almost 100. So that is the key difference when we using the fixed time and prescribed time controllers. We have talked about the difference between the fixed time, the prescribed time cooperative controllers, and we have applied those cooperative controllers into different application areas. The first application area is what we call the dispersion. In the middle, you can see there is a different number of green circle, number of different and green circles, and in the middle there is a red one, and that indicates a group of robots initially closely located in the center. And our target is to disperse all those green circles, the robots, to spread out in the whole area, and at the same time building a high quality communication flow. And the final configuration is showing on the right hand side. You can see all those different all those green circles, they have been spread out to cover the whole area, and the communication flow has also been built for the purple agent. That is for the dispersion. Next, we also investigated some flocking. Okay, so different from the consensus, flocking it means robots, they initially have different velocities. The arrow, you can say they pointed to different directions, indicate they have different velocities. After applying our designed time guaranteed controllers, at the end, the all on the right hand side, you can see all those arrows, they are in the same direction, indicating, their velocity matches each other. They achieve the flocking at the end. So this is the flocking. Next, we also apply our controllers to achieve the formation control for a number of robots in the lab. And here we're doing some experiments showing a group of 6 robots, one as the leader, 5 as followers. After about 190 seconds, the team can build a pentagon formation. And we also apply the controller to the application area of deployment. This is quite similar to the previous application of dispersion, but in this case, we consider 2 different groups, and those 2 groups will merge and to cover a big area, and also build some communication flow to make sure the communication quality between CS1, the control station 1, and the control station 2 are reliable. And also we have applied our cooperative controllers in smart grids. For smart grids, the target is to achieve some frequency regulation and active power sharing among the distributed generators using our, for example, in 2025, we publish our latest results in this area using some fixed time secondary frequency regulation controllers to achieve the frequency regulation and active power sharing for the microgrids with some disturbances. Also, our approach is fully distributed without using any global information. And also, I want to emphasize we have applied our controller to cable-driven robots, and this is a very interesting topic that has been done when I was in Sweden between 2020 and 2024. And you can see this is a project between, it's a interdiscipline project. It combines civil engineering and automation engineering. We design some cable robots and to achieve some 3D concrete printing. And I have a small video here. You can see in the middle there is an effector, and that has been controlled by eight cables. It can move very smoothly in the lab. And in the middle picture, it shows we also do have already printed some concrete sample. But because in 2024 I moved to Auckland, so it's this project discontinued when after I moved to Auckland. But anyway, this topic I want to say it's really interesting. It's the first time we use some control strategy integrate with the civil engineering techniques. So that is cable-driven robots. Now, I have talked about a lot in the cooperative control of multi-agent system. Now let's move to the second part. I would like to focus on introduce the application to the connected automated vehicles. So vehicles is, as mentioned before, for multi-agent systems, that agent can be a lot of things, the robots, drones, underwater vehicles. So here we consider the vehicle, the automated vehicle as a type of agent. So here we modeling this kind of vehicle using a third order dynamics. So tau I times uh, the the third derivative of pi plus the second derivative of pi equals ui plus omega I. So this is the model we used for the automated vehicles. Of course, for the vehicles, you can use some other dynamics to describe the system. And also in the system, we label the leader as the vehicle 0, and it involves according to some specific control input of U0, and U0 denotes some unknown but bounded control input. And also we need to define the spacing, or we call the ranging policy. So here each follower vehicle I in this team is required to follow its predecessor I minus 1 while maintaining a desired inter-vehicle distance we call di I minus 1. And also we use another notation of di as the desired distance. And here we consider the very simple spacing policy, the constant spacing the constant spacing policy, which means the I minus 1 equal to D0. So next we consider the information flow for this the vehicle team. And so two different cases are considered. The first case is we call the undirected communication topology. On the second case, we consider the directed communication topology. So those two different cases, the main difference I can here show you like using the A34, the communication link between the vehicle 3 and the vehicle 4. When we investigate the undirected case, that A34 will be equal to A43. Okay, that's undirected. But on the other hand, if we consider the directed case, then we can only have A43 assigned to that specific link, which means when we have A43, the A34 may not exist. It can be 0 or some other numbers, but here we can only guarantee A43 is a positive number indicating the communication strength between the vehicles 3 and 4. So, and so here we formulate the problem. And the objective is to design a cooperative planning controller UI for a group of n vehicles despite the presence of external disturbances and model uncertainties, finally to achieve the goal of on the following two goals. On the left is shows when t bigger than the uppercase t, the velocity and the acceleration between each vehicle and the leader is 0. And on the other hand, we want to make sure that the team, all the n vehicles, they can maintain a desired inter-vehicle space, which means the inter distance between I minus j. So here pi minus pi minus 1. So the distance will be equal to I minus j when t bigger than the uppercase t. So this is the problem. Now, the main results. Here, we make the design in two steps. Step 1, we design some distributed observer. In this slide, you can see here the key feature is we introduce some time varying parameters, the alpha 1t, alpha 2t, alpha 3t. These three parameters, they are time varying because in conventional this kind of control design, usually the time invariant parameters are used. So here the key difference is we introduce these alpha 1, alpha 2, alpha 3, the time varying parameters. And based on the observer, we further construct a nonlinear variable Si in this form, it equal to EAI plus an integral term. And based on this Si and the previous observer, finally we can design the controller in the bottom. And here for UI, you can see we also have another time varying parameter, alpha 4t. Okay, so this alpha 1, alpha 2, alpha 3, and alpha 4, they are to be designed later. Now, the main result of theorem 1, we can design those four time varying parameters in this showing in this slide. Of course, here we consider two different cases. The first case is the p larger than 1. The second case is when p is in between 0 and 1. So for different p, we design the different time varying parameters for alpha 1, alpha 2, alpha 3, and alpha 4. And finally, the 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 planting problem can be solved using using the design controllers. Okay. Next is when previously we are talking about the planting control under the undirected topology. If the topology change to the directed case, we need to redesign the controller. And again, step one, we design some distributed observer for each vehicle I. Here very similar to the previous one, we also introduce three different time varying parameters of alpha 5t, alpha 6t, and alpha 7t. And based on this observer, the new cooperative planting controller under the directed topology is designed in the form of UI on the right-hand side. And when those four different time varying parameters are designed in the form of alpha 5, alpha 6, alpha 7, and alpha 8, again, for two different cases of p larger than 1 and when p in between 0 and 1, we assign different time varying parameters, and finally the planting problem can be solved under the directed topology. And next we show some simulation results. So the simulation results, we consider a group of 6 vehicles. As mentioned before, we have 1 leader vehicle and 5 follower vehicles. And during the planning driving, an external disturbance is added to the system dynamics. And the acceleration command A0 is implemented in this on the left hand side, and also some parameters of the vehicle are selected on the right hand side. And you can see here when the topology is undirected, which means we set the Aij equal to Aji, and both they equal to 1. When the communication link between vehicles I and J are built. And BI, another notation where we assign a constant number of 1 to it when the vehicle I can have direct information access from the leader. Okay, so on the right-hand side is the simulation results. You can see with the constant spacing between every two consecutive vehicles is achieved at about time of t equal 6.5. And meantime, the velocity and the acceleration of each vehicle can also track those of the leader when t larger than 6.51. So this is for the undirected case. Next, when the topology changed to some directed case, we consider two modes. The first mode is we call the predecessor following PF mode, and the other is the leader predecessor following the LPF mode. So those two modes are very typical in the connected automated vehicles. And both modes, they belong to the directed communication topologies. And on the right-hand side, it's the simulation results under those two different modes, communication modes. Okay, so next I would like to discuss some of the research directions. Because today's topic is the time guaranteed cooperative control. So one very promising future direction would be the control under some real-world network imperfections. Okay, which means that right now most of the work has been done under some ideal network conditions. For example, when we consider the communication between vehicles I and J, once the communication link been built, we consider the communication can be done over time. But in reality, that communication link can be broken due to some, like, for example, the battery shortage or some other unexpected scenarios. Those kind of communication links can be broken. So that is one thing we need to consider. So how to design this kind of time guaranteed control under the real world network imperfection really deserves some further investigation. For example, for example, developing maybe some prescribed time cooperative control under the random uh, communication delays. For also like as mentioned, when some communication links be broken, the lossy communication, and also some asynchronous the event-driven control updates. So all these kind of network imperfections, under this kind of imperfections, how to design the time guaranteed control deserves some further investigation. So that is the first one. Next, the second one, it's about the integration of some learning-based methods with the time guarantees. We all know that nowadays, a lot of AI tools. Also in our simulation, we have used a number of different parameters. Usually, we tune these parameters trial by and error approach. Okay, which means those when we select those parameters, usually they are not the optimized one. With the AI tools, a lot of data, we can use those kind of AI help us optimize those vehicle parameters or the robotic parameters to achieve some better system performance, which means we want to combine some machine learning or AI techniques with the provable time guarantees. Okay, for example, we can investigate some the safe reinforcement learning techniques with prescribed time constraints and data-driven estimation with fixed time control. So this is the second future direction. Another possible future direction would be the scalable coordination for large-scale autonomy. So nowadays, a lot of research in the cooperative control of multi-agent systems still focus on some small scale, not like for example, you consider a team of 10 drones or 20 drones. It's still a small number. Okay, if we have a large scale multi-agent system, for example, you have 1,000 drones, how to achieve the coordination. We also this direction is very interesting, and also in this kind of large scale multi-agent system, you may have some different agents. Okay, for example, in a big team, you can have cars, drones, the underwater vehicles, a lot of different agents in the system. So how to design the new cooperative controllers in this kind of scenarios really deserves some further investigation. Also we may introduce some hierarchy control. We can make those large-scale multi-agent system into different layers, and we can achieve design some controller inside each layer, and also make sure for different layers they can interact with each other. So all these kind of things, the scalable coordination for large-scale autonomy is an interesting future direction. So all these three directions are for the future research. Okay, so this is the end of my presentation. Thank you so much.
All right, thank you. Thank you very much, Boda, for your excellent presentation and talks. So
Thank
I
you.
believe that your talk should be very helpful for all of the webinar attendees, because I think most of the attendees are from the researchers or students from the universities. I think particularly for those researchers who are doing research in the control areas or in the autonomous vehicles areas. Yeah. So now I think is our question and answers section. So for our attendees, if you have any questions, queries, feel free to ask and discuss with Boda. Any questions?
Hi, hi, Boda.
Hello.
I was just wondering, with your modeling for CAVs, have you considered which protocol base you're using? Like, do you think it would be more of a Wi-Fi DSRC, or do you think it would be more of a cellular
Thank
application?
you. Thank you for your question. To be honest, for me, I'm more focused on the control side. Your question is more like from the communication part side. I'm not expert from the communication, but I can tell when we're doing some experiment, because we did some experiment before, and we did use the Wi-Fi for the communication between different robots.
Okay, cool. Thank you.
Thank you.
Any other questions from our audience?
Hello, Boda. Thank you for your presentation. I have one
Thank you.
question. In multi-agent system, how we will ensure that outputs are authentic from each the agents? Like if there is conflict, how we will manage the conflict from each agent's output, or how we will verify the output between them?
Verify. I mean, okay, so let's use this vehicle for example, and our target is to make sure the output, for example, the position, the location, the velocity, and the acceleration, they all match for each vehicle. They all match that of from the leader. So that is how we verify. We can make sure the error is approach to zero when the time t is larger than a specific time constant.
All right, thank you. But if there is, for example, if there is conflict between multiple agents output, then how we will do this, or how we will handle this?
Conflict. Sorry, what I didn't.
Like, for
So what?
example, if
Hmm,
multiple agents are
mhm.
giving conflicts in their output.
Mm, we want the output to converge to reach some agreement. But your question is asking the output not to reach the agreement.
Yes.
our target is to design the controller to make sure they can reach the agreement. And okay, of course, we need to consider some constraints we call the state constraint or the output constraint. We will add some, for example, the barrier functions to make sure those the states and the output they are within some boundaries. We do have some strategies to process the constraints.
All right. Thank you, Boda.
Thank you. Thank you.
Hello, Boda.
Hello.
This is Man. I actually got some questions regarding the experiment you did. Because
Okay.
usually in the experiment, it may involve like the time delay during the communication, or there might be some model mismatch.
Yeah.
I'm not sure if you did see some like the difference of the time constraint you mentioned during the simulation and the experiment. Did you
Yeah.
consider like the time delay or the model mismatch when you did the experiment? Then the second question is there any the time difference when you finish the experiment? What's the difference?
Yeah. Thank you, Meng, for your question. You ask a very good question. In fact, we also notice this kind of problem for our theoretical design and the real-world implementation. For example, I mentioned we did some experiment using a team of 6 robots in the lab. We did the simulation first. We found out that the coordination can be achieved within, for example, 5 seconds. But when we're doing the experiment, in this case, it takes about 190 seconds. You see the difference. Of course, as you mentioned, they will have the communication delay. They will have because to to get the coordinate, we use some cameras. That image process part also consumes some time, and also the computer itself, the calculation takes some time. So as a whole, which means in experiment, the time does not match the simulation, and we have clearly pointed out this in our paper. If you have interest, you can have a look. We clearly mentioned that that is, I think, it belongs to some physical limitation, and of course, we want to improve the experimental results, but I would say it's not easy. But we know the problem. We do have a plan to reduce the gap between the simulation and experiment. Thank you.
Yeah, thank you so much. I think probably if we can find, for example, the specific time delay and what's the hardware limitation, probably we can get like the lower bound of the time constraint for the experiment as well, right?
Yes, that is possible. Yes.
Because
Because
I'm
right now
considering.
I didn't
Hmm.
add the time delay term. I didn't do the time delay analysis.
Hmm.
Yeah, as you mentioned, we can theoretically add some delay term in
Hmm.
our
Hmm.
when we design the controller and to find out some bound
Yes.
yeah, that is a good future direction, I would say. Yeah.
Yes.
Thank you.
That's the reason I consider, for example, like the other applications, as you mentioned, for
Mm,
the car following, probably the time constraint may be important, because not for the
yes.
robot case, then we can
Mm,
specify or calculate the exact or the analytical time constraints time for that
yes.
application. Yeah, thank you,
Yes.
thank
Yes.
you. Very
Thank you.
interesting
Thank you, Mark.
topic.
Thank you, Mo.
All right, thank you, Boda, for answering all of our audience questions. So now, any more questions from our audience?
Uh, Hello,
Hello.
Doctor. You mentioned the event trigger in your future work,
Mm,
and then in my opinion, you you can't communicate all the time. So if this will influence your
Yeah, I got that. The event trigger design, if they here in most of my results, I'm considering all those agents. They can continuously communicate with their neighboring agents, which is not realistic. In practice, you have to consider some communication issues, as you mentioned. So, but I think there are already some researchers have done the event trigger control. If you only consider the event trigger control, it's not. I would say it's not a significant contribution. You have to consider a number of different communication restrictions, consider them together. For example, you may also add the time delay and the event trigger and also the topology change. A lot of things you need to consider together to make the problem more realistic. That is can be a good future direction.
I think the event trigger control maybe will influence the time guaranteed control.
Yes, of course. As because right now the results I mentioned, I mean our published results all considering the continuous communication. So if you have the you bring the event trigger design, for example, you will have to make some sacrifice. For one, the time, the convergence time. The other is the tracking error. So you have to make some sacrifice. You need to balance the two performance. You know, you cannot achieve good results from every single aspect. You have to balance those.
Thanks.
Thank you.
All right, thank you. Boda, so I have the few queries and questions. So basically, the first one is regarding your fixed time and prescribed in time, right? So from the practical implementation point of view, so have you done any like the investigation on the real, the difference between the fixed time and prescribed time? So any big difference from the practical experiment or practical implementation point of view?
Thank you, Hai, for your question. Yeah, very good one, because nowadays a lot of papers they are doing some, they want to implement on the real world experiment. So from my experience, we did apply to using the fixed time one. We haven't used the prescribed time one. The reason is you can see the difference is the time varying one, the prescribed time one, they use the time varying controller, which means it can bring some singularity issues. I believe you're also aware of that. That can cause some problems. Theoretically, it's okay, it's very smooth at some specific points, but in practice, I didn't do the experiment, but I would assume there will be some challenges for the singularity issues.
Okay, all right. So this is you have already give some like the potential, right? So problems once we implement the prescribed time control for the practical case. All right, yeah, no problem. Thank you. So for the second question is regarding the connected automotive vehicle simulations. I think I recognize in the simulation you give the external disturbance to describe by using the sinusoidal signal. So am I correct?
Yeah.
Yeah.
Yes.
So in the practical case, how to simulate this kind of the external disturbance? Because for those kind of the automated vehicles when they drive on the freeway, so normally, so have you done any investigation which kind of practical disturbance that we meet, like the strong wind or sine wind, etc. So in that case, how can we simulate this kind of disturbances? How can we evaluate the
Yes, thank you,
impact
thank you,
or the
thank you,
yeah.
Hai, for your question. Very good question. A lot of reviewers also ask me this kind of things. Yeah, to be honest, we just add, if we only add that sign function, it will not be very realistic here, because here that paper was published 2, 3 years ago. At that time, it's okay, but nowadays, if you consider the sign as disturbances, I would think it's very difficult. A lot of reviewers will challenge you. And I would say one possible more reasonable disturbance can be as you mentioned, all of a sudden a strong wind, or like some other drivers, they come into your lane. That can add some, maybe the abrupt, the how to say, we can add a big magnitude of, like, in simulation at some specific constant, yeah, during the time, not like the sine function.
All right, yeah, because this is we need to find the gap between the simulation and the experiments, right? Particularly when we implement the connected automated vehicle in the real scenario.
Yes, yes.
Okay, yeah, great. Thank you. So my final question regarding your future work. So you mentioned that we can implement AI machine learning for
Yeah.
this kind of as the one of the good research directions. But considering the real, like the consumption, energy consumption point of view. So are you able to give us some, like, the insights on if we actually implement the AI machine learning, because of that, lots of data will be used for the next step in control. So in this case, should we upgrade the hardware, the system, or should we consider the energy consumption as one of the issues? Yeah. So are you able to give us some the insight on this
Uh,
point?
Thank you, Hai. I would consider your question from another aspect here. I would more consider the secure things. Nowadays, a lot of the AI tools, they do the training using the cloud. I would think we may need some local training hardware to make sure it's secure, because potentially, because a lot of attack can happen, and also some due to some privacy issues. We need to make sure it's secure. We do some, so I would say we would prefer to do some local training to optimize those parameters.
All right. Yeah, that's good. The information that should be very helpful for us. Yeah, no problem. Thank you. Thank you very much, Boda, for your
Thank you.
detailed elaborations for all of our the questions. All right,
Thank
so
you.
I
Thank
think
you.
that's probably all for today's the webinar. So finally, I would like to sincerely appreciate for Boda's time and contribution to our first webinar. And thanks very much again, Boda, for your very excellent presentation
Thank you. Hi.
and talk. So now I would like to, before I end for today's the webinar, I would like to give some quick post. So now let me share with the screen. So for all of our the webinar attendees and the members and non-members, so please keep in mind we have already created our formal LinkedIn account for IEEE VTS WA chapter. So please feel free to add the IEEE VTS WA chapter and follow the account, because in the future when we will regularly organize the technical events and activities, normally monthly, in a monthly way. So please follow this LinkedIn account to keep an eye for the future events. And we also have VTS W chapter email if you have any queries, if you want to make some the technical contributions, or even you would like to organize some like the student events or activities. Feel free to reach us by using the this email. And finally, because for each monthly technical webinars or seminars, we will record for all those sessions. So after each of the technical events, so this video will be uploaded to this YouTube channel. So if you want to share, if you want to watch those the videos, those talks on at the other times, feel free to go to the YouTube channel and watch. All right. So basically, that's all for today's the webinar. So I appreciate for everyone, particularly for Dr. Boda, the contribution time. So let's keep in touch, and I am looking forward for everyone to joining our future events and technical activities. So enjoy the rest of the day, and looking forward to see you again next month. Thank you.
Thank you,
Thanks,
Han.
everyone.
Thank you all. Thank you, everyone.
Thank you.